Hello dear children, in today's class we will be discussing the whole chapter of calorimetry. Dear children, in this chapter we have two units. Mainly in a unit A we will be discussing about the concept of heat, temperature, factors affecting the heat and thermal capacity, specific heat capacity and their applications, principle of calorimetry and calorimeter. Whereas in unit B, we will be talking about the change of state, melting point of ice, boiling point of water, specific latent heat of fusion of ice and its applications. So these are the main topics which we are going to cover in this today's video. Children, first of all, think about the substance, whatever it may be. It might be a solid or a liquid or a gas. For the sake of our convenience, let us take a substance in the solid state only. Children, we all know very well that every substance is consisting of a molecules. Means here, what I mean to say is that to understand the concept of heat, children, we need to think about the microscopically. So for that, now we are going to think about the molecules which are there in the substance. Children, each and every substance are having n number of molecules. But for sake of our convenience, just we are going to consider the 3 molecules. It doesn't mean that substance has 3 molecules. Just to have a clarity, just to get a command on the content. Okay, fine. Children, each and every molecule in the substance is in very important state of vibration. State of vibrations. So due to this state of vibration, children, each and every molecule will possess some kinetic energy. At the same time, children, each and every molecule will exert some force on neighbor molecule, which means what? There are some intermolecular force of attraction. So due to the intermolecular force of attraction, each and every molecule will possess potential energy. Children, every molecule has potential energy and as well as kinetic energy. Kinetic energy is due to the state of vibration, whereas potential energy is due to the intermolecular force of attraction. So it is very clear that the molecule in a substance has some potential energy and as well as some kinetic energy. This sum of the potential and kinetic energy of the molecule of a substance only we can call it as a internal energy. We can call it as a internal energy, which means what, children? Each and every molecule of a substance has some internal energy, So as per this discussion, children, so each and every molecule has some internal energy. Let us say the internal energy of this molecule is I1, this molecule is I2, this molecule is I3. Now children, can we get total internal energies of a molecule, what we can say substance? Yes, we can get. How? By adding all these internal energies, which means what, children? The sum of the internal energy of a molecules of a substance is called thermal energy. This is very important, which means what? If you can add all internal energies, for suppose there are n number of molecules in a substance, then children, how many internal energies will be there? Yes, In. In is what? Internal energy of the nth molecule. Internal energy of the nth molecule. If you can add all this, which means what? The sum of the internal energies of a molecules of a substance is called, children, thermal energy. Children, this is a very important. Thermal energy. So this thermal energy only will decide whether it is a hot body or cold body. Is it clear? Fine, children. Which means what, children, here? Hot body has more thermal energy, whereas cold body has less thermal energy. Is it clear, children? Now children, what happens if hot body is brought in a contact with the cold body? Let us see here. For suppose, children, here, let us say this is hot body. Let me write here, it's a hot body is brought in contact with the cold body, children. Then obviously we can notice that, children, cold body warms up whereas simultaneously hot body cool down. This happens only when some energy flows from hot body cold body. Why? Because here hot body has more thermal energy, cold body has less thermal energy. When these two bodies with a different thermal energies are brought in a contact, what is happening? The energy is flowing from hot body to cold body, due to which cold body warms up whereas hot body cool down. Children, this energy which is flowing from hot body cold body only, we can call it as a heat energy, that is heat. I make clear, very important. Which means what here? Heat is nothing but the form of energy only. Heat is a form of energy. Heat is nothing. Heat itself is energy which always flows from hot body to cold body. Is it clear, children? Fine. Now, what are the SI units of heat, children, here? So, SI units of heat are joules. SI units of heat are joule, whereas CG units of heat are calories. And how these two are related is a very important examination point of view. Children, here 1 calorie is equal to 4.2 joules or 1 joule is equal to 0.24 calories. So, this is the minimum knowledge we should have regarding the heat. Okay, children? Fine. Fine. Now, children, so it's a very clear that when hot body is brought in a contact with the cold body, definitely what is happening? Heat energy is flowing. But how long will it take place, children? Yes, till both bodies attain thermal equilibrium. Children, it's very important. Till both bodies attain thermal equilibrium, children. Once both bodies attain thermal equilibrium, then what happened? This flow of heat stopped. Is it clear? Fine. And here one important thing actually. So, children, if any kind of equilibrium you want to talk, you want to say that one system is in equilibrium, there must be one physical quantity must be same for both bodies. That's very important. So, in this case, we are saying the thermal equilibrium. Two bodies are in thermal equilibrium. Then what is that physical quantity which remains same for both and which indicates the state of thermal equilibrium? So, that physical quantity is nothing but what, children, here? Temperature. Is that clear? So, temperature is the what, children? It is a which indicates the state of thermal equilibrium. So, this is what actually the original definition of the temperature. Of course, already we know the one more definition is there. What is that here? The degree of hotness or coldness of a substance is called temperature. Yes, it is also right only. Is it clear? Fine, children. And we know that temperature is measured by a device called thermometer. Then what are the units, children? Yes, we know that here temperature is measured in a Kelvin and as well as in a degree Celsius. And children, the examination point of it is a very important conversion of temperature. Children, very important. So, it is a conversions of temperature. So, here mainly we have temperature of conversion from Kelvin scale to Celsius scale to Kelvin scale. Here 2 points we need to remember. So, that we are going to discuss now. Look at here, children. First, suppose, children, you want to convert from degree Celsius scale to Kelvin scale. Try to understand. Then what we have to do? We have to add 273. Whenever you want to convert from degree Celsius to Kelvin scale, we have to add 273. So, which is example. So, here example. So, 50 degrees Celsius, you want to convert into Kelvin. Then what we have to do here? 50 plus 273. So, this is going to be 323 Kelvins. Very simple. Okay, fine. And here second one, children, here. If you want to convert Kelvin scale to degree Celsius, then minus 273 we have to do it. Okay, fine. So, it is going to be like this. So, example, let me tell you example. For suppose here 73 Kelvins. So, you want to convert it to degree Celsius. So, what we have to do? 73 minus 273, which is minus 200 degrees Celsius. Okay, children, this is how we can convert. So, we can write a general formula for this. So, for this, children, here temperature in a degree Celsius is equal to temperature in a Kelvin scale plus 273. This what actually general formula which we can use, or you can write like this: temperature in a Kelvin scale is equal to temperature in degree Celsius minus 273. So either of one you can use. It depends whether you are converting what we can say Celsius to Kelvins or Kelvins to Celsius. It is okay. This is about the temperature. It is just about the temperature. Now, how about change in temperature? How about change in temperature? Change in temperature. Children, we all know very well that here there are 100 divisions in a Celsius scale, whereas 100 divisions in a Kelvin scale also, which means what? The number of divisions in a Celsius scale are equal to the number of divisions in a Kelvin scale, which means what, children? It's very, very important here. The rise in temperature or fall in temperature in Kelvin scale is equal to the rise in temperature or fall in temperature in a Kelvin scale. Is it clear? Fine. So what we can say here, change in temperature in degree Celsius scale is equal to, Celsius scale is equal to the change in temperature in Kelvin scale. Children, don't get confused. Here we are talking about the change in temperature. Here just temperature we are talking. Just temperature. So this how can we understand? Example, children. Example. For suppose here is an object, here is a body. Okay. So we are supplying some heat. Let us say initially it is at 5 degrees Celsius. Now it has reached to 25 degrees Celsius, let us say. So there is some rise in temperature. So what is that rise in temperature, children, here? That is, the rise in temperature will be delta T is equal to 20 degrees Celsius. Now the question is that what is the corresponding rise in temperature in Kelvin scale? I mean what here, children? So this is the rise in temperature in a Celsius scale. But the question is what, children? What is the corresponding rise in temperature in a Kelvin scale? Children, surprisingly here, delta K also 20 K only. Try to understand. Means either rise in temperature or fall in temperature is same in Celsius scale and as well as in a Kelvin scale. Is it clear? Just copy it. Yes, children. Now, once again, let us recall about the state of thermal equilibrium. Children, when two bodies are in thermal equilibrium, what does it mean? It means that both bodies have same temperature. But children, it does not mean that both bodies have same amount of heat. This is very, very, very clear. Children, two bodies are at the same temperature. It doesn't mean that both bodies have same amount of heat. So, which means what actually? So, the amount of heat, okay, the amount of heat, either it is amount of heat is absorbed or released, it depends on few factors. It's very important. Now, let us see, children. So, the first one is that here, the amount of heat absorbed or liberated, it depends on nature of the substance. Nature of the substance means what, children? Different substances will absorb different amount of heat, and here it also depends on, the amount of heat absorbed or liberated also depends on the mass of the substance. Depends on mass of the substance. How does it depend, children? So if more is a mass, more amount of heat energy required. If less is a mass, less amount of heat energy is required. Okay, fine. And the third is that it also depends on the change in temperature, children. It also depends on the change in temperature. Change in temperature of the substance. That is what here Q is directly proportional to the delta T. Let us say equation 2. Children, from this equation 1 and 2, so we can write Q is proportional to the M delta T. Children, whenever there is a proportional symbol, it can be replaced with a constant. Here we are going to take a constant as C. So Q is equal to, we can write M C delta T. Children, this is very, 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 very important formula. Here, what is C here? C is a specific heat capacity. So about this which we will discuss. So first let us concentrate on the importance of Q is equal to MC delta T. Children, this is a formula which we use to calculate the amount of heat energy gained or lost. It's clear. But here one condition is there. This formula is applicable only when there is a change in temperature. Children, I repeat once again. This formula is used to calculate the amount of heat energy required. But the condition that there must be some change in temperature. Then only we can use this formula. Clear? Fine, children. Now, let us discuss about the thermal. Let us discuss about the thermal capacity. Thermal capacity, or we also can call it as a heat capacity. Thermal capacity or heat capacity. Children, this we use letter C dash to represent. Why? Already C we are using to represent specific heat capacity. So now we are discussing about the thermal capacity or heat capacity. Okay, children, fine. Let us see here. For suppose here, let us take some substance, some substance. It might be 1 gram, 10 gram, 20 gram, 30 gram, what it may be. Whole substance we are taking. Let us say, children, initially it is at 10 degrees Celsius temperature. Initially at 10 degrees Celsius temperature. Now, I want to increase this temperature to 11 degrees Celsius. So, here we are raising the temperature, children. So, in order to raise the temperature of a body, what we have to do? We have to provide some amount of heat. Let us say we are providing some amount of heat. For what? To raise the temperature by 1 degree Celsius. Am I right, children? 1 degree Celsius or 1 Kelvin. Why 1 degree Celsius or 1 Kelvin? Because it is a change in temperature. Change in temperature is same in Celsius scale and as well as in Kelvin scale. Okay, children, fine. So now let us define the thermal capacity or heat capacity. The amount of heat energy required to raise the temperature of whole body by 1 degree Celsius is called thermal capacity or heat capacity. If M is the mass of the substance and Q is the amount of heat required and delta T is the rise in temperature, then children, here thermal capacity is defined as Q by delta T. Children, this is a very important formula. Now let us see here, what are its SI units, children? Joule per Kelvin. Joule per Kelvin. And what are its CGS units? CGS units are calorie per, what we can say, degree Celsius, or you can use Kelvin also, because this represents what? Change in temperature is the same in a Celsius scale and as well as in a Kelvin scale. Is it clear? Fine, children. Now here thermal capacity depends on two factors, children. Here it depends, thermal capacity depends on two factors. First one is mass of the substance, depends on mass of the substance, depends on mass of the substance, whereas second one is very important. What is that here? Nature of the material, nature of the substance, nature of the substance. And here how can we understand this mass of the substance, children? For example, you can take a 10 grams of copper and 100 grams of copper. Both are having same nature, but as they are different in mass, they will have different thermal capacities. Is that clear? So, this is about thermal capacity or heat capacity. Now, we will see one best example which is very important for examination point of view. How the question is given, children, based on this I will tell you. So, here if the thermal capacity of an object or substance is 50 joule per Kelvin, what does it mean, children? It means that, see, we have to provide 50 joules of heat energy to that substance to raise the temperature by 1 Kelvin. Is it clear? So, this is the meaning of the thermal capacity. Children, it depends on nature of the material and as well as what, children? Mass of the substance also. So, how does it depend on the mass of the substance, which we will discuss after discussing about the specific heat capacity. So, now we discuss about, see, till now we discussed about this heat capacity. So, heat capacity for a unit mass of a substance is called specific heat capacity, which means what? We are specifying the mass, unit mass we are taking. So, here let us think here. For suppose, children, here some unit mass of a substance is taken. How much it is? Unit mass, strictly unit mass only, strictly, children, unit mass of the substance is taken. For suppose initially at 5 degrees Celsius. Now, we want to raise it to 6 degrees Celsius, which means what here? Rise in temperature is 1 degree Celsius. To do so here, we have to provide some amount of heat we need to provide. This amount of heat energy required only, we can call it as a specific heat capacity. Which means what, children? Which means what here? The amount of heat energy required to raise the temperature of unit mass of a substance by 1 degree Celsius or 1 Kelvin is called specific heat capacity. But mathematically, how to calculate? Children, as we already know that Q is equal to mc delta T. From here, we can write C is equal to Q by m delta T. Children, this is a formula which we have to use to calculate the specific heat capacity. And children, here SI units. So here SI units are joule per kg Kelvin, or CJ units are, children, here calorie per gram degree Celsius. And the very important point about this specific heat capacity is that it is a characteristic property of a substance, which means what? It doesn't depend on the mass. You can take 1 gram of water, 100 grams of water, 100 kgs of water. The specific heat capacity will be same. Why? To calculate specific capacity, we will consider unit mass only. So it is different for different substances, but it is same for a same substance, though mass is different. So it is a constant. Clear? Fine. Children, here, and one important thing is that here water has highest specific heat capacity. Children, water has highest specific heat capacity. What is its value? Its value is 1 calorie per gram degree Celsius, or we also can write 4200 joule per kg Kelvin. 4200 joule per kg Kelvin. Is it clear? Fine, children. And here, let us see how specific heat capacity is related to the heat capacity or thermal capacity. Children, we know that here C is equal to Q by m delta T. So this I will write like this: 1 by m into Q by delta T. Children, Q by delta T is nothing but what actually? Thermal capacity. So here C is equal to 1 by m into C dash. From here we can write C dash is equal to m into C. Children, this is very, this is the relation between, in exam they will ask a question, write the relation between heat capacity and specific heat capacity. Children, you better write in the wordings. Okay, how you should write? Thermal capacity is equal to mass into specific heat capacity. Children, as I told you that heat capacity, that is the thermal capacity, depends on mass, right? Now let us take an example so that you will understand. Children, first suppose, children, here, so as I told you that water specific capacity is 1 calorie per gram degree Celsius. Okay, so now I am taking mass of 10 grams and I am taking here mass of 200 grams. Mass of 200 grams. For this, I want to calculate the thermal capacity of, see, children, strictly talking about the water only. So thermal capacity of 10 grams of water, thermal capacity of 200 grams of water. How it will be? Will it be different or will it be same? Let us see here. So thermal capacity is equal to mass into, that is 10 into specific capacity of water is how much? 1 calorie per gram degree Celsius, that is 1. So this will be 10 calorie per degree Celsius. Whereas for this, let us calculate here, that is C dash is equal to mass is how much? 100 into specific capacity of water is 1, which is equal to 100 calorie per degree Celsius. Children, here is water, but they are different mass. That's what I am telling you, that thermal capacity depends on mass. That means same substance, if it has different masses, so it will have different values of thermal capacity or heat capacity. Clear? Fine. And here two more important points. Hope it is copied, children. Just copy it. 3, 2, 1. Yeah. Fine. So this is how a specific heat capacity and heat capacity are related. And here, children, very important. So from this, as C is equal to Q by m delta T, for a given amount of heat, for a given amount of mass, children, C is inversely proportional to the delta T. Very important. Which means what, children, here? See here, delta T is what here? Delta T is either rise in temperature or fall in temperature. Rise in temperature or fall in temperature. So which means what here? the substance with high specific capacity will show low rise in temperature or low fall in temperature, whereas the material with low specific capacity will show more rise in temperature or more fall in temperature. Let me give you an example. For suppose children, let us take a copper. The specific capacity of copper is 0.4 calorie per gram degree Celsius. Whereas let us take a water. Water value is 1 calorie per gram degree Celsius. So it's very clear that specific capacity of water is greater than that of the specific capacity of the copper. But children, in these two, which one is the best conductor? You think which one is a bad conductor? Very clear, undoubtedly you can say that it is a conductor. It is a best conductor. And here is what is a conductor of heat. But where is a bad conductor of heat? Bad conductor of heat. So with this we can conclude one important thing. What is that here? So for conductors, the specific capacity value is less, whereas for poor conductors, let us not use a word called bad. Bad means something will get to our mind. It's not a bad. Let us use it's a poor conductor. Poor means I am not talking in terms of money also. Poor conductor of heat, which means what here? See, the material with high specific capacity, okay na? So it does not allow the heat to pass through it, rather it absorbs. Whereas the best conductors will have low specific capacity. Whereas the poor conductor of heat will have more specific capacity. Clear? Fine. Now let us see children. So let us think about the application part. That's what I am telling you here. So application part also based on this relation only. If you can understand this relation, then everything will be very, very easy. Children, the substance with high specific capacity will show low rise in temperature or low fall in temperature. The best example you can take as water only. So water is having high specific capacity. So due to the high specific capacity of water, we will have so many applications. For example, if you can see the coastal regions, so the temperature is moderated. So it is just due to the high specific capacity of water, and water is used as a coolant, and water is used as a heat reservoir. Even children, farmers also fill the fields during the winter cold nights, will fill their fields with the water to protect the crop. What could be the reason? So because water has high specific capacity. Children, this we are not discussing what we can say in detail, because as it is a one shot video. So if you want in detail explanation for each and every topic, just links will be given in the description. Just go through those links so that each and every topic, topic wise and unit wise, it was discussed. Is it clear? Fine children. So this is all about heat capacity, specific capacity, and how they are related. Now children, one more important topic is that principle of calorimetry. Children, very, very, very important. What is that means? Principle of calorimetry. Children, so this principle of calorimetry is based on law of conservation of energy. Law of conservation of energy. Children, let us recall once again what is law of conservation of energy. According to law of conservation of energy, energy neither created nor destroyed, but it can be transferred from one form to another form. Okay na? So in exam they'll ask you a question, on which law does principle of calorimetry base? So it is based on law of conservation of energy. And what is another name given to this? What is another name for a principle of calorimetry? It is also called as principle of method of mixture. Why are we calling principle of method of mixture? Because whenever means we will be adding different substances with different masses with different temperatures. We are mixing, we are adding. Then we will see how the heat transaction will take place. Clear? Fine. So three basic questions we can expect. On which law does it base? It is based on law of conservation of energy. What is another name given to it? So it is given the principle of method of mixture. Then how can you state? So they may ask you a question, state the principle of calorimetry. So for this children, to understand this, let us take a hot body. Okay, let me just take a little bit big. So here, this is a hot body of mass m1, its specific capacity is c1 and its temperature is T1. Okay, is brought in a contact with a cold body of mass m1, specific capacity C2, temperature T2. So let us say a hot body and here is a cold body. Children, what will happen when two bodies with a different temperatures are brought in contact? Obviously, we know that there will be a heat flow from hot body to cold body, which means what here? Cold body warms up, hot body cool down. Means what? Don't you think that here hot body is losing the heat? Simultaneously, cold body is gaining the heat? Yes, it is happening. So, it states that children, the heat lost by the hot body is equal to the heat gained by the cold body. Heat gained by the cold body. Again, I repeat. Heat lost by the hot body is always equal to the heat gained by the cold body, provided there is no heat loss to the surroundings. Provided there is no heat loss to the surroundings. Clear? Fine. And here we need to understand one more important point. As hot body is losing the heat, obviously there will be a fall in temperature. But how to calculate that fall in temperatures? Look at here. Delta T1 is a fall in temperature of the hot body, whereas delta T2 is a rise in temperature of cold body, children. So how to calculate this delta T1? It can be calculated as T1 minus T, whereas here it is T minus T2. Here you may get wonder, sir, what is this T called? Yes. So as I told you that hot body is brought in contact with the cold body, heat start flowing, but till what extent? Both bodies attain thermal equilibrium. So at thermal equilibrium, what will happen? Both bodies have a same temperature, so called resultant temperature. So here children, T is the resultant temperature of the two bodies when they are in thermal equilibrium. So this resultant temperature is less than the hot body temperature, greater than the cold body temperature. That is how we calculate the fall in temperature of hot body, gain what we can say rise in temperature of cold body. Now children, how to calculate the heat loss by the hot body? Yes, we know the formula, right? MC delta T. Let us apply MC delta T. Here M1 C1 delta T1 is equal to M2 C2 delta T2. Let us substitute delta T1 delta T2 here. It will be M1 C1 T1 minus T is equal to M2 C2 into T minus T2. So if you can exchange the term, finally you will get we need to calculate resultant temperature, right? So here T is equal to, we will get M1 C1 T1 plus M2 C2 T2 by M1 C1 plus M2 C2. Children, this is a formula which we use to calculate the resultant temperature when two bodies with a different nature, different masses, different temperatures are combined or mixed. And here you may get wondered, sir, what would happen? What will happen if both bodies with the same nature are added? For suppose hot water, most will be getting exam, what is the numericals? Hot water, okay, with M1 mass, T1 temperature, and cold water with M2 mass and a T2 temperature, which means what here? As both are water only, both nature is same. When both nature is same, specific heat capacity also will be same. Why? Specific heat capacity depends on its mass. When both specific heat capacity are same, in a numerator you can take C as a common, denominator you can take a C as a common. So both C's will get cancelled. So here you can get T is equal to M1 T1 plus M2 T2 by M1 plus M2. Children, strictly we use this formula to calculate the resultant temperature when both bodies have same nature. Clear? Okay, just copy this. Fine children. Now we discuss about the last topic in the unit A. What is that actually? Calorimeter, children. So here children, what is a calorimeter? First of all, on which principle does it work? Obviously you can guess. Yes, what is that, children? Yes, calorimeter works on the principle of calorimetry. What is the use of the calorimeter, children? So calorimeter is used to find the heat lost or heat gained. Okay, fine. So here this calorimeter is nothing but what, children? It is a cylindrical thin copper vessel. Cylindrical thin copper vessel is called actually what we can say a calorimeter, children. So then how the calorimeter will be? In a simple terms, I'll tell you here. You can see even on the board also the picture. So children, here look at it. So it is cylindrical copper vessel. I think let me write properly. So simply it is a copper glass. Okay, na? So don't say copper glass. Okay, na? So it is cylindrical thin copper vessel. So children, why are we using copper vessel? Why are we using copper vessel? Because it has less specific heat capacity. Why thin only, children? Because as its thickness is less, its mass is less. Its mass is less, it has low thermal heat capacity, low what you can say thermal capacity or heat capacity, which means what? It does not keep heat in it. Whatever the heat is there, that is given to the ingredients. Is it clear? Fine, children. And the thing is that, children, whenever we are using a calorimeter, so there will be heat loss, obviously. See, let us think of practically, not an ideal case. So let us, if we think about the practical case, definitely always there will be some heat loss. So we cannot stop this heat loss, but we can minimize the heat loss. So if you want to, learn how we are going to minimize the heat loss, first we should know that. So in which process, that heat is going to be lost actually. So children, there are three modes of what we can say heat transfers, in which actually there will be a heat is like so going to the atmosphere, there will be heat loss actually. Okay, so what are those three modes, children? Here three modes of transfer of heat. There are three: conduction, induction and radiation. So how to minimize the heat loss due to the conduction, children? So to minimize the heat loss due to the conduction, this calorimeter is placed in what, children? Wooden box. Very important. It is placed in wooden box, and these gaps will be there. These gaps are filled with the insulating material, very poor conductor of heat. So to minimize the heat loss due to the conduction, we are going to keep calorimeter in a wooden box, and also the gaps between the calorimeter and the wooden box are filled with what? Insulating material. That is fine. Then how can we minimize the heat loss due to the conduction? To minimize the heat loss due to the conduction, children, this calorimeter is going to be closed with wooden lid. It is going to be closed with the wooden lid, and here two holes are provided in order to keep what, children? A thermometer, and as well as one stirrer will be there, and here one stand will be there, holder is provided to hold the thermometer. That is fine. But how can we minimize the heat loss due to the radiation, children? So here materials cannot stop the radiation, right? Yes, because radiation can penetrate easily. So for the radiation, a medium only not required. So for that, children, what are we going to do? Children, this inner surface of calorimeter is polished. Means it is polished in a smooth manner. Then what happens? If heat will try to escape in the form of radiation, it gets reflected. Means here multiple reflection will take place in it only. In such a manner, what happened? The heat is trapped. So this is how we can minimize the heat loss due to the conduction, convection and radiation. Clear? Fine, children. Now we discussed about the change of state. And what is a change of state, children? The process of change from one state to another state at a constant temperature. The process of change from one state to another state. It might be solid to liquid, liquid to gas, gas to liquid, liquid to solid, but at a constant temperature is called change of state. Children, here means how can it happen? How can we achieve this change of children? By providing heat or by removing heat, we can change the substance from one state to another state, but at a constant temperature. Now children, first of all, look at here. So here let us say solid. So here is solid. Children, if we are heating, when we heat this solid, then what happens? It will convert into liquid. Obviously, it will convert into liquid. So this happens at a constant temperature. This what we can say process only we can call it as a melting. We can call it as a melting. And further, if you can heat, then this liquid change into gaseous state, will change into gaseous state at the same temperature. This process is called boiling. This process is called boiling. This is on heating, children. But when we cool, what will happen here? Again, this gas will convert into liquid. This process at a constant temperature, this process is called condensation. This is called condensation, or it is also called as liquefaction. And further, if you can cool, liquid convert into solid, this we can call it as a freezing. This we can call it as a freezing. So in some cases, what happens? Solid directly changes into gaseous state. This only we can call it as a sublimation. We can call it as a sublimation. The process of conversion from solid state to directly gaseous state. So which substance will show, sublimation? Example, ammonium chloride, naphthalene, iodine, camphor. These will show the sublimation. Children, on cooling, what happens again? This gaseous state, gas will convert into solid state. This only we can call it as a solidification. We can call it as a solidification, or we also can call it as a deposition. It is also called as deposition. Children, I am telling you, this happens. See, this change of state happens at a constant temperature. Clear? Function. And one important thing, for a pure substance, the melting point is equal to the freezing point. The best example, children, the melting point of ice is 0 degrees Celsius. Then what is the freezing point of water? 0 degrees Celsius. Then you make it one doubt. Sir, melting point and the freezing point are same. Then what makes a difference? Yes, children, there is a difference. What is that? During the melting, heat is absorbed, whereas during freezing, heat is released. Is it clear? Yes, children. Now we discuss. Hope it is copied. Fine. Now we discuss what is a melting, what is a melting point, and on which factors this melting point of a given substance depends. So children, now we are going to discuss melting. What is a melting, children? The process of conversion from solid state to liquid state at a constant temperature is called what, children? Melting. Then what is a melting point, children? The constant temperature at which solid changes into liquid is called melting point. So now we will see how volume will change during melting, children. During melting means what? Heating, children. But do you think that all substances will expand in heating? No, it is not possible, children. So look at here, children. For suppose materials like lead and wax, children. Yes. So here what will happen, children? In the case of these substances, on melting, what happens, here, these substances will expand. These substances will expand, which means what here? Volume increases. Volume increases. But on the other hand, children, let us take a substance like ice. It's very, very important. So here on heating, during what we can say, it's a melting, this ice will contract. Ice will contract, which means what here? Volume decreases. It's a very, 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 very important. Okay, fine. So this is important to understand. Why it is important to understand? Then only we can understand the what we can say effect of pressure on melting point of substance. Melting point of substance. Children, look at here. So what happens? Now let us see the factors on which melting point depends. First one is a pressure, children. First one is a pressure. Children. Fine. So in the case of a substances which will expand on heating, in that case actually what happens, children? Melting point is directly proportional to the pressure. But whereas in the case of a substances which will contract during melting, in that case, children, here melting point is inversely proportional to the pressure. Children, examination point of view, melting point of ice is a very, very, very important actually. Examination point of view I am talking. So here they will ask you a question. What is the effect of pressure on melting point of ice. Then what we should write, children? So melting point of ice decreases when we increase the pressure. So this is the effect of pressure. Okay, fine. Effect of pressure. First one is over. Now second, children, what is the effect of impurities? Impurities. Children, impurities means don't think something which is bad. Not that actually. So when you are drinking a milk, if you can add a sugar, then that sugar is an impurity in that milk. Okay. With the addition of impurities, what will happen? Children, when you add impurities to the ice, then its melting point decreases. Very, very, very important. So melting point of ice decreases with the addition of impurities. Clear? Fine. So example, let us say that. So in general, we know that the melting point of ice is at 0 degrees Celsius. But children, when you add salt to the ice, this we can call it as a freezing mixture. This we can call it as a freezing mixture. Freezing mixture, which is used in the making of kulfis, and its temperature falls to minus 22 degrees Celsius. Okay, children, examination point of view, again I repeat, examination point of view, effect of pressure, effect of impurities on melting point of ice is important. So when you increase the pressure, melting point of ice decreases. When you add the impurities, melting point of ice decreases. In both cases, it decreases. Clear? Fine, children. Now here, one more important thing is that here, heating curve of ice, children. So here, heating curve of ice during melting. First, suppose, children, look at here. Let us take ice, children. It will be at a 0 degrees Celsius. It will be 0 degrees Celsius. Now, when you start heating it, do you think that complete ice disappears immediately, it will form water? No. Slowly it start melting. Means there will be a stage where you will have ice plus water. It is ice. This is ice plus water. Then what happens? You will form water. Means till even whole ice melts, till whole even small gram of ice, small piece of ice also there is just about to melt. Till that time, the temperature remains same. Once whole ice converted into water, then still you are heating, then temperature starts increasing actually. Now for this, how the heating curve will be there. Can I erase this? Nobody's copied? Yes, children, examination point of view, this heating curve of ice on melting is very important. Look at here, children. So here, let us take it to 40. Children, so for this actually what you do, just you can take ice in a beaker and start heating it. At the same time, simultaneously note on the temperature, children. So what do you notice, So initially the temperature of ice will be 0 degrees Celsius. So this is the point you get. Okay. After 30 seconds, same temperature. After 60 seconds, after 90 seconds, same. Means depends on the how much amount of heat you are taking and how much amount of heat which we are providing. Means what I mean to say that till whole ice converts into water, the temperature remains same. Means here, from here to here, children, this is a ice plus water. Ice plus water. Once whole ice converts into water, then what happens? Then temperature starts raising. So this is how you will get a curve. So this you will get. So this is purely it is a water. Purely it is a water. Straight curve. So that water temperature will be rising. So children, this is a heating curve of ice on melting. Just copy it. This examination point of it is very, very important. Yes. Now we discuss about the boiling and boiling point. Children, what is a boiling, children? The process of conversion of liquid state to the vapor state or gaseous state at a constant temperature is called boiling. What is the boiling point, children? The constant temperature at which liquid changes into vapor is called what, children? It's a boiling point. For a pure water, what is the boiling point, children? For a pure water, boiling point is 100 degrees Celsius. For pure water, the boiling point is 100 degrees Celsius. Now we discuss on which factors does the boiling point of a water depends. Okay, children, fine. So here, the first point, so during boiling, how the volume will get affected? Yes, obviously, volume will increase during the boiling. Fine. Okay. Now boiling point of water depends on the boiling point of water depends on the first factor, children. The first factor is pressure. First factor is pressure. First factor is pressure. Children, at a normal temperature and a pressure, generally at a normal pressure what will happen? So water boils at 100 degrees Celsius. But children, the moment when you can take a pressure cooker, okay na? So let us consider the pressure cooker. So in a pressure cooker, children, in a pressure cooker, what happens? So water boils around 120 to 125 degrees Celsius. 120 to 125 degrees Celsius means generally we know that water boils at 100 degrees Celsius only, but instead of a pressure cooker, what will be the boiling point? Boiling point is increased to around 120 to 125 degrees. What could be the reason? Because inside pressure is more. Inside pressure is more, which means what here? Boiling point is directly proportional to the pressure. When you increase the pressure, boiling point increases. When you decrease the pressure, boiling point of water decreases. Effect of impurities, children. Effect of impurities on boiling point of water. Children, it's a very easy to understand this all. This actually, impact of what we can say impurities on boiling point of water. Children, when you add impurities to the water, what happens? Boiling point increases. Boiling point increases. So what is the example here, children? The example is if you can take a seawater. Actually, if you can take a seawater boils around 115 degrees Celsius. Seawater boils around at 115 degrees Celsius. Children, just you can compare melting point of ice, boiling point of water. So melting point of ice in both cases decreases. When you increase the pressure, melting point of ice decreases. When you add the impurities, melting point of ice decreases. Now think about the boiling point of water. In both cases it increases. When you increase the pressure, boiling point of water increases. When you add the impurities, boiling point of water increases. So this is how we can remember. Fine. Okay. Now the last topic in this chapter is latent heat. What is the, children? It's a latent heat. Children, so let us recall once again about the change of state of ice actually, children. So look at here. For suppose here is the ice at 0 degrees Celsius. Children, when you start heating it, do you think that the entire ice suddenly changes into water? No, it is not like that. So there will be a state where there is a combination of ice and water. It is a combination of ice and water. It is also 0 degrees Celsius. And next what will happen? So you get the water which is also at 0 degrees Celsius. Means just ice melts. Whole ice just melted. Try to understand till that what we can say till that time also the temperature remains same. But in this entire process, are we not providing the heat? Yes, we are providing the heat. This is a very, very important point to understand. Means here what is happening here? There is a change of state, children, here. So during the change of state, what is happening is very, very important. Here 2 points we need to understand. Children, before going to that, let us think about the relation between temperature and kinetic energy. How both are related here? Children, here when you increase the temperature, kinetic energy increases. When you decrease the temperature, kinetic energy decreases. Which means what? Kinetic energy is directly proportional to temperature. So, but during the change of state, don't you think that here temperature remains constant? Yes, temperature remains constant. Then obviously kinetic energy also remains constant. Then what will happen, children? Yes, here potential energy increases. Potential energy increases. What will happen? The intermolecular force of attraction decreases. So due to which what will happen here? So for potential energy increases. So during this change of state, children, what are the heat which we are supplying? That is hidden in the form of a potential energy. So that hidden energy only we can call it as a what we can call it the latent heat. So how to define the latent heat, children? So latent heat nothing but it's a hidden heat. The heat which is provided during the change of state is called latent heat. But in exam, if they'll ask you a question, state or define a latent heat. How to define? The amount of heat energy required to change the substance from one state to another state at a constant temperature is called latent heat. Then what is this specific latent heat, children? So when you can, when you can define latent heat for a unit mass, then you can call it as a specific latent heat, which means what here? Let us say just unit mass is taken. Let us think as just a unit mass is taken. Just what it's a unit mass is taken. Now let us define the same manner it is. So the amount of heat energy required to change the substance, of unit mass, from one state to another state at constant temperature is called specific latent heat. Okay children, fine. For suppose here m is a mass, q is the amount of heat supplied, then specific latent heat is defined as mathematically q by m. Children, here look at here, the SI units are joule per kg, whereas the CGS units are calorie per gram. Children, from here only can we express like this, q is equal to ml? Yes children, yes. So this is the formula which we use to calculate the amount of heat energy required. Then you may get a one doubt, sir, we also have q is equal to mc delta t. Then you also said that this is a formula which is used to find the amount of heat energy required. Yes children, both formulas are used to find the amount of heat energy required only. Then what makes the difference, children? This formula is used to find the amount of heat energy required when there is a change in temperature. This formula is used to find the amount of heat is required when there is a change in state but there is no change in temperature. This is a point which we have to remember. Is it clear? Fine. Now children, the last point is what? Specific latent heat of fusion of ice. So let us talk strictly for ice, children. For suppose it is a ice, so 1 gram of ice. Okay, so we want to convert 1 gram of ice at a 0 degree Celsius to 1 gram of water. Children, then how much amount of heat must be provided? For this 80 calorie amount of heat energy required. So here specific latent heat of fusion of ice. So how to define specific latent heat of fusion of ice, children? The amount of heat energy required to change the 1 gram of ice at a 0 degree Celsius to 1 gram of water at 0 degree Celsius is called specific latent heat of fusion of ice. Its value is how much, children? Its value is 80 calorie per gram. Children, what does it mean? It means that 1 gram of ice at a 0 degree Celsius absorbs 80 calorie heat to convert into water at 0 degree Celsius. Children, as we know, 1 calorie is equal to 4.2 joule. So it also can be written as 336 joule per gram. 336 joule per gram. Children, here, so because of this high specific latent heat of fusion of ice only, we have some applications. Let us discuss, children. So before that, children, here, look at here. So what is that here? 1 gram of ice at 0 degree Celsius, whereas ice cold water, or else 1 gram of water at 0 degree Celsius, which has more heat, and give reason. Examination point also very, very important. So look at here. So 1 gram of ice at 0 degree Celsius will convert into water, 1 gram of water at 0 degree Celsius, when you can add 80 calorie heat when you are giving. So in a reverse manner, let us think here, children. So when you can freeze the water at 0 degree Celsius to ice at 0 degree Celsius, what happened? Don't you think that it releases 80 calorie heat? Yes. As it is releasing, which what? It has 80 calorie heat in it. So which means what? The water at 0 degree Celsius has more heat than that of the ice at 0 degree Celsius. Because of this reason only, children, ice at 0 degree Celsius is preferred over ice cold water at 0 degree Celsius to cool the juice. For example, if you want to have some drink, children, so in that, would you like to prefer water at 0 degree Celsius or ice at 0 degree Celsius? Obviously, ice at 0 degree Celsius only, because the moment when you can add ice to that drink, what happens? Ice has to melt. In order to melt ice, 1 gram of ice will take a 80 calorie heat. Like that, you imagine this much amount of ice you are adding. So to melt such a that much amount of ice, children, it needs more amount of heat. From where it will take? It takes from that particular drink only. That is the reason why that particular drink will get cooled faster. Okay, now fine. So because of this reason only, when you are eating the ice, children, what happen? A kind of soothing pain you will get. Why? The moment when you try to crush the ice, you are increasing the pressure, due to which what happens, children? It melts. To melt the ice, it requires heat. From where it will take? It will take from your body. Is it clear? Fine, children. And even after the hailstorm, generally what happens? The surroundings temperature will fall down like anything. What could be the reason? So during the hailstorm, you can find some ice piece on the earth's surface, right, in your premises. But after some time, do you see the same ice pieces? No, they'll melt. But here one point we need to understand: to melt that ice after the hailstorm, from where the ice cubes are getting heat, means that ice takes heat from the surroundings. That's what the surroundings temperature will fall. Clear? Fine. And one more point. What is that? So if you can go to the what we can say, cold countries, children. So cold countries, yes, it's quite natural of having the frozen lakes. So when the frozen lakes are, children, when they are melting, then obviously premises will get cool like anything. Why? Because to melt the what we can say, to melt that ice, they have to take heat from the surroundings only. But in reverse manner, you can think why? While forming the frozen lake, while forming this frozen lake, the surroundings will become warm. Why? Children, during melting, heat is needed. So they will take heat. So surroundings temperature will fall down. But during freezing, heat is released. That heat is added to the surroundings so that the surroundings will become warm. Yes or no? So these are the few applications of high specific latent heat of fusion of ice, children. So children, so this is these are the topics in a shortcut we tried. I think almost it is around, might be plus also. Okay, but try to understand such a big topic. It is a calorimetry. We try to complete in a one shot. Children, if you want in detail videos on the calorimetry, just links will be given in the description. Just kindly go through it. Okay, children, fine. So children, after listening class, just go through books, or before listening class, what it may be, it's your option. But the thing is that just kindly read the textbook. So every time I tell you, read the textbook. That is the ultimate source, that is the standard source for you to get a command on the content. So read the textbook. So while reading the textbook, just maintain a notes so that you can note down some important points and try to learn the exercise, what we can say, example questions given, example numerical solved, and especially the numericals based on calorimeter are very, very important. So after that, just you can go through the exercise questions so that you will have a good practice and you will be ready to write the exam like anything, and you will do the best. Okay, children, thank you so much. All the very best.